Welcome to the Senior Design 2 Group 9 final demo video on the Digital Pixel Helmet platform. Our advisors are Dr. Chan from SD1 and Dr. Wei from SD2. These are the team members of Group 9. Hi, my name is Joshua Soriano and my major is Electrical Engineering.
I'm Vince Doe. I'm an electrical engineering major.
Hi, I'm Devin Schuck-Snyder, an electrical engineering major.
I am Ryan Hauk, and I am an electrical engineering major.
In this midterm demo, we will be presenting 5 different parts. Part 1, the engineering specifications. Part 2, the overall system design. Part 3, the overview of all parts and subsystems. Part 4, the overall functionality. And Part 5, engineering specifications in detail. The 3 engineering specifications for this project are startup time under 5 seconds, touch response under 100 milliseconds, and accurate microphone signal to noise performance under 100 milliseconds. The DP-HP is a wearable entertainment helmet centered around a programmable LED visor and synchronized ear lighting. The system supports static graphics, animations, scrolling text, and other visual effects. It also includes microphone-based sound reactive displays, while the companion app and capacitive touch controls allow the user to switch between the different operating modes. To make the helmet safe for any user to wear, we decided to place all the PCBs inside of a separate book bag with cutout holes for PCB wiring and mounted connectors for quick disconnecting to troubleshoot the helmet and book bag alone.
The helmet's companion application subsystem is a more advanced and convenient tool for controlling the LED matrix visor compared to the capacitive touchpads, and it also includes customization options for the various display modes and their presets. Their connection protocol is facilitated through Bluetooth Low Energy.
For our current LED progress, the pre-built 8x32 matrix was fully operational and controlled by the ESP32. We have successfully implemented static graphics, scrolling text, and multiple repeating animations. The system can also switch between different visual presets while it's running without needing to restart the controller. This confirms that the main LED control software and display functions are working correctly. The final touch to the LED subsystem are the LED pre-built PCBs from Amazon. These PCBs are programmed to just have a rainbow effect going clockwise on each ear. Our audio amplifier subsystem is a board with an LM386 powered by a 5-volt regulator. 2 speakers are connected in series through the signal line of the LM386 to help achieve a surround sound experience while wearing the helmet. We saved audio wave files in the ESP32 to play back through the speakers once the capacitive touch actions were activated. Here's an example of next preset.
Next preset. Next preset.
Now previous preset.
Previous preset. Previous preset.
And the last example showing an indication of when the helmet is on and which mode it is in.
Helmet ready. Demo mode.
In this test, I'm using an electronic load to verify that my LM2576 3.3 volt buck regulator can supply up to 2 amps of output current, and I'm supplying it with a 12 volt power supply. Before testing, I measured the 3.3 buck output directly with a multimeter to confirm that our buck regulator is properly outputting 3.3 volts. At 0.5 amps, the voltage drop is 0.02 volts. At 1 amp, the voltage drop is 0.03 volts. At 1.5 amps, the voltage drop is 0.05 volts. At 2 amps, the voltage drop is 0.06 volts. Overall, our regulator's output voltage only decreased from 3.28 volts at 0.5 amps to 3.22 volts at 2 amps, which is a 0.06 voltage drop, and that shows that our regulator is working properly. Next, I am testing my 5-volt buck regulator, which is also being powered by a 12-volt supply. Before testing, I also measured the 5-volt buck output directly with a multimeter to confirm that our buck regulator is properly outputting 5 volts. At 0.5 amps, the voltage drop is around 0.03 volts. At 1 amp, the voltage drop is 0.05 volts. At 1.5 amps, the voltage drop is 0.07 volts. At 2 amps, the voltage drop is 0.09 volts, and so far our buck regulator is working perfectly. In this test, I am verifying that our MCU PCB can receive a regulated 3.3 volt supply from our LM2576 regulator. To confirm this, I measured the input voltage of my MCU board using a multimeter. Since a multimeter reading displays 3.3 volts, this shows that the MCU board is properly receiving power from the 3.3 volt regulator output. Right now, I am testing our battery indicator. I'm using the power supply to replicate our 12-volt battery. Due to our battery chemistry, our maximum voltage is 15 volts, and the lowest voltage is 10.5 volts. I turn on the battery indicator by holding the touchpad for 2 seconds, and the LEDs last for 3 seconds. At 14 volts, 6 LEDs are green. At 13 volts, 5 LEDs are green. At 12.5 volts, 4 LEDs are yellow. At 12 volts, 3 LEDs are yellow. At 11.5 volts, 2 LEDs are red. At 11 volts, 1 LED is blinking red.
Here is our charge controller PCB and the battery data displayed on the mobile app. The battery level and charging indicator are determined by two ADC GPIO pins right here, which are green wires, that check the overall voltage of the battery and the charge controller's battery temperature input pin, respectively. This data is sent to the app to be displayed at the top of the screen as seen here. The battery level is a simple percentage while charging the indicator, while the charging indicator is an icon that tells the user whether the helmet is being charged or not. Here it is, a demonstration.
The capacitive touch is intended to be a set of external controls to control the helmet without using the app. There are 2 electrodes, one located on each ear of the helmet. For functions, it can navigate between presets and modes. There are 6 modes: demo mode, text mode, graphics mode, animation mode, sound mode, and group mode, which all have multiple presets contained in them. For the capacitive touch, the left electrode goes to the previous preset or group, and the right goes to the next. Holding for 2 seconds changes the mode, except for microphone mode, which can be entered into from any mode by holding either electrode for 4 seconds. Tapping the right or the left goes forward or back for presets in one of these individual modes. Lastly, holding the touchpads for 2 seconds activates the battery indicator LED strip, which flashes and then shuts off after 3 seconds. The microphone is another feature of the helmet. It will take in noise, whether that of the user's voice or the surrounding environment, and display it on the LED matrix in different animations. We use several software level techniques to filter and make the output clean. Once the microphone mode is selected via app or the capacitive touch electrode, the LED visor grabs the output of the microphone and displays it. The first mode is a simple sound wave mode, and we have a few other audio reactive presets that display the sound and cool in different ways. See, look at that. Look at how cool it is. Look at how cool that is, buddy.
Here's the companion
Ooh,
application. We start with a handshake between it and the helmet. It automatically searches for the BLE server, connects, exchanges security keys, and discovers the services of the helmet before entering the main app screen. Here we can see the current display mode of the helmet, text mode. We can enter the text mode and start moving through the presets with the capacitive touchpads. But we can also move through the presets with the app. But we can also have the added feature of saving them. You can also change the color of the text. And this is instantaneous, and it can be done multiple times. And now we move on to the other presets, such as graphics. Here in graphics mode, we can change to this particular mode, cycle through the presets like before, or if we want to, we can cycle through the long list of presets in the drop-down menu and get this preset and add it to a group. And then we can do the same thing for animation mode. We can start from the top. We can move to a particular one, and then it'll actually go to the specific animation preset. And then we can go to sound and go through these presets and see that they react. And then finally, we can go to group mode, and it goes to the preset we created, or at the very least we customized for this.
The first engineering specification we evaluated was startup time. Our design requirement is that the helmet completes its startup sequence and enters normal operating mode in less than 5 seconds after power is applied. To evaluate this specification, we used a 2-channel oscilloscope. Channel 1 monitored the 5-volt power rail supplied by the regulator, while Channel 2 monitored the LED data line entering the visor matrix. Startup time was defined as the elapsed time from the power was applied until the startup loading animation finished and the helmet entered its normal operating mode. This definition was chosen because the loading animation is part of the system's initialization process, and the helmet is not considered fully operational until that sequence is complete. The measured startup time was approximately 4.4 seconds. This test was repeated 10 times, and every trial remained below the 5-second requirement. Based on these results, the startup time specification successfully passed.
This test verifies the response time of the capacitive touch subsystem. Our design requirement is for the capacitive touch to respond quickly enough that the user experiences a near immediate visual feedback from the LED display upon triggering a touch event. To measure this, I connected channel 1 of the oscilloscope to the MPR121 capacitive touch controller's IRQ pin output shown in yellow. Channel 2 is connected to the LED control signal shown in green. When the touch sensor detects a touch, the IRQ pin changes state, indicating that a touch event has been recognized by the controller. The ESP32 processes this interrupt and updates the LED subsystem. Using the oscilloscope cursors, I measured the time difference between the touch interrupt and the LED response. The measured response time in this run was about 40 milliseconds, as indicated by the delta value on the oscilloscope. The measurement demonstrates the delay from touch detection to visual response, including interrupt generation, software processing, and the LED update. Since the measured response time is about 40 milliseconds, the capacitive touch subsystem provides a fast and responsive user experience and satisfies our system performance requirements. Here is our data from the 10 test runs. The standard deviation is about 3.21 milliseconds. The average is about 45 milliseconds, and the variance is about 10.3. For our microphone subsystem, we wanted to test SNR as one of our engineering specifications. The rating of the optimal SNR for the microphone that we're using, an electret microphone using the Max 9814 audio amplifier, is 61 decibels according to a datasheet. However, that's a proper professional laboratory setup. So given the noise of the full system integration of our system and the fact that we're not using professional testing equipment and setups such as calibrators, we are aiming for an SNR of 40 or maybe even lower. However, since the Max 9814 has automatic gain control and we cannot change the automatic gain control since we are using a breakout board instead of a custom PCB, the SNR is likely to be lower and the dynamic range lower, as automatic gain control aggressively deadens loud sounds and magnifies minute sounds. We ran a code in Platform I/O to determine the SNR as best as possible, display it on the serial monitor, and then we test optimal SNR using a 1000 Hz tone from a tone generator at the loudest volume we can, since many microphones are tested with a 94 dB SPL tone at 1 kHz. So we let it level off and then we play the 1 kilohertz tone. And then you stop playing the tone and let it level off again. Of course, it reacts to speech and stuff. And then we're going to level off again. And then we're going to play the tone again. And that's it. So after 10 tries, this is the data we have. We have a standard deviation of 1.8. We have a mean of 21.5. And we have a variance of about 3.37.
Thank you for watching the final demo of the DPHP project. We hope you enjoyed.